Good morning, ladies and gentlemen. Yes, there's feedback somewhere. I'll try again. Good morning, everyone. Welcome to Stellenbosch Faculty of Engineering. I'm Hubert van Eden, the head of Department of Industrial Engineering. So from my side, as Tinus' home department, welcome, but also from the faculty side. I think a large portion of what you'll see today is actually more a faculty initiative than an individual department or two. A couple of people, I see a number of familiar faces and also people from different sides of Cape Town. So welcome to all of you. Gideon from Gabs, welcome Gideon. I think there's a lot you are pioneering that's starting a lot of the things that we're going to discuss. Then from TETA, I think Mashabane Letwaba, I didn't see him yet. Then Antoni van Rensburg from Western Cape Government. Also from City of Cape Town, Johan Anderson. And then also from our colleagues from UCT and other universities. Professor Zeitgeest, welcome from UCT as well. In terms of, I always tell Tinus in these things, I've got two hats on. I myself, my focus is on logistics and supply chain management. That's my research focus. And as of lately, a lot of it goes into system-wide planning of freight with electric vehicles. So it's, although I try not to mix in with Tinus's passengers, we cannot, it's the same platforms, the same backbone that we need in terms of energy, vehicles, charging infrastructure, etc. So a lot of touch points. So I'm listening today, not as head of department, but also as researcher as part of this group. I'm looking forward to hear what we have installed today. So Tinus, over to you.
Thanks, Hubert. Thank you, everybody, for being here on time. I'm a bit of a timing freak, and it's wonderful to have to us on time. I just want to double check that the audio is going through to the online session because we've got a few people online as well. Yes, it's fine. Okay, so as Hubert said, he's looking forward to listening to what people are going to present. I am too, because I've not been around for the last few days, and I've asked my students to compile some of the research that we've been doing. I think the most important thing to know about today is probably where the toilets are. So they're through there and down the passage to the left. And then the second most important thing to know is I'm not going to allow questions. I know it's irritating, and I know some of you will have questions, but what I find is oftentimes the people who ask questions are those who just want their voices heard, right? So what I suggest we do is ask questions during the tea break and during the lunch break, and you can go and engage with the researchers and ask the questions that you have there. To set the scene, before we start to present, we're on a very tight schedule, so I'm going to try to keep it quick, but I want to give you an overview of the research that we do and explain maybe the context of what the results that you'll be looking at today entail. I've told the students, each one of them, you need to keep it to 10 minutes, and I want you to focus on the stuff that really matters to the people from industry and from government. So hopefully it'll be useful to you. But our research focus is very much on transport that is fit for purpose for the sub-Saharan African conditions. I don't think it makes sense for us to focus on transport that's fit for other areas. Otherwise, we're just going to waste time and waste money. So we focus on buses, minibuses, and motorbikes. Those are the predominant modes of transport in sub-Saharan Africa. Although all of you arrived this morning, one person in a vehicle, that's not the norm, and that's not how we should travel. So firstly, minibus taxis, they're all across sub-Saharan Africa. So this is a mode of transport that move the majority of people. And unfortunately, it's the vulnerable and the poor, which means they don't get enough attention. The other part of the transport sector that we try to focus on is also motorbikes. You may not appreciate or know this, but in the rest of sub-Saharan Africa, this is actually the main mode of transport. 2 million of these in Kenya, and it's growing fast. Stefan will say something about this later. And we also look at other modes of transport, as you see there. But when you think we have a problem with 60/60, when you get to a stop in Kigali in Rwanda, this is the site. This is the site that you see. You've got motorbikes filling the gaps between vehicles, and this is how people are moved. It's not just goods, it's actually how people and goods are moved. So just to give you an indication of what things are used for, they're used for mass people transit, so 4 people on a bike there. I think that was Halloran taking the picture. It's also used as a tow-in truck. That's a bike on a bike. And it's also used for furniture removals. So these things are really ubiquitously used for anything. Building supplies, as you can see there, gas canisters, and this taken by Heath a month ago in Kenya, again, building supplies. So it's a real mode of transport that moves people. Obviously, what we know is the last mile delivery, and that is also some of the work that you'll see this morning. So we'll present some work on last mile delivery, but also on what they call boda bodas. It's these motorbikes in Kenya. And in our lab, which is, the future is slightly uncertain. We'll find out a bit more next week. But what we try to focus on is, first of all, just to keep people moving. But we're also asking the question, how is mobility impacted by electrification? And to what extent does the mobility patterns that we observe lead to a burden on the electrical infrastructure? Because in the rest of the world, they slap vehicles, electric vehicles, onto the system, and their grids can carry it. But in our case, we have limited generation capacity. We have old and aging and fragile electrical infrastructure, which means a lot of our work is on that as well. We try to also consider the environmental impact. Again, sub-Saharan Africa is a weird beast. When you go electric, you don't necessarily reduce the carbon emissions that the vehicle emits just because you're shifting the burden onto Eskom, and Eskom tends to be coal dependent. So in future, absolutely electrification makes sense from a CO2 perspective, but currently, as you'll see, not necessarily. One of our big concerns, especially if I can quote Andrew in the front here from Balancel, our big concern is, will our children be able to live in this country? And one thing to get that right is we need the jobs, we need the skills to transition to electric mobility, because we can't block it, we can't prevent it. Also worried a lot about costs, especially because we're looking at the vulnerable users of transport, and obviously they're much more sensitive to price increases. Does electrification result in a cheaper mode of transport? And then finally, something that very few people look at is health. Even though our CO2 emissions don't really reduce, or CO2 emissions don't really reduce with electrification, the air quality definitely improves. And something that most people don't realize is if you go into a township today, the exposure level that the children have because of the poor air quality has the same impact as severe malnutrition. And I think that's something that definitely needs more attention. The particulate matter enters bloodstreams and it stunts children's growth. So some of the results that you'll see today is Joshua will be presenting on how viable is it to go electric with minibus taxis. Also be presenting quite a lot, all of them, on the impact on the grid. Just what does the load profiles look like? To what extent can we mitigate that load profile and shift the loads into the times when there's low energy demand? We'll present some environmental results, so CO2 results, and also present some, some air quality results that you can ponder. If at any time you want to look into this deeper, I sent a PDF out to everybody who's here. You can also go and look at just ev.sun.ac.za publications and have a look at all the publications if you struggle to fall asleep at night. In terms of the jobs and skills, we're working with TETA, the Transport Education and Training Authority, looking at training and educating. So the reason why maybe you weren't informed as well as where you need to be this morning is because I was teaching at the City of Cape Town, teaching taxi owners on electrification of bus fleets, for example. So a large part of what we do is information transfer and building skills. So what Waldo will be demonstrating a bit later, just after lunch. So this is a way to get you back from lunch into the room. Waldo will be demonstrating our test bench here, which is more like a training bench, explaining some of the electrical principles of electric mobility. So we've done a lot. I don't want to boast too much, but we've published substantially in the last few years. Since 2020, we've almost published 50 journal publications in this group. Not a big group, 12 conference publications. And we've had publications in some of the best journals in the world. So the work that we do is relevant, and it's evidenced by the fact that we're publishing in places where people want to read. And what is also maybe just important to note is we've been doing quite a few projects on the side. So we've been working on taxis and buses. We've been looking at charging facility, charging infrastructure with Sanedi and through the European Union. We've also looked at some projects with the World Bank. Stefan will be presenting on driving behavior stuff that we did, training motorbike drivers on safe driving. And we've also, as I said, developed quite a lot of skills. I think very important to mention at this point, we have one big funder right now, the Western Cape government. They're funding some of our research, and they've given us freedom to look at 4 or 5 different areas and projects. And truth be told, we really struggled to get funding. If it wasn't for them, if it weren't for them and TETA, we would have closed shop. And we're facing that again towards the end of the year. So if you're wondering why you're here, it's not because I'm begging for money. It's because Joanna contacted me. Are you here, Joanna? I haven't seen you. From the city of Cape Town contacted me, and she said they want to come and see our lab. And I said, you need to come quick because we're probably going to close shop before the end of the year. And I invited 10 people, and then suddenly it exploded into this interest. So we're presenting the stuff that we're presenting, showing you that it's relevant, but we are kind of dwindling at this point. And a special mention again to Andrew from Balancel, who's knocked on many doors and shouted at many people to try to get us funding. Okay, so we're going to start now. Each presenter has 10 minutes. And then, as I say, they're going to transition as quickly as they can. If it's your turn to speak next, please come to the front so you're ready. And here we go.
Can you hear me? Is that all right? Cool. Morning, everyone. My name is Halloran Stratford, and I am focusing largely on the motorcycle, the two-wheeler side of the research in the sub-Saharan African context. And basically, my research is centered around this observation that replacing ICE motorcycles with electric ones would require proper planning in terms of grid loads and resource requirements. Because we know that our grid is questionable and this is an expensive operation. So the research question that has been set out is, it's quite wordy, but it's basically how can fleets of electric motorcycles with swappable batteries be modeled and simulated using large data sets with different charging configurations and energy sources to plan for the electrification of commercial two-wheeler fleets in resource-constrained sub-Saharan Africa. Now you'll see I highlighted 3 words there: simulated, data sets, and configurations. And in amongst all of this wordiness, those are the 3 things that are really important in this pipeline. It needs to be centered on data. The simulations tell us the answers such as grid load and resource requirements. And then there's also different configurations that we set up to try and test different scenarios. So firstly, there's 3 main data types that we use. Firstly, origin destination data, not ideal just because it would be good to know the routing between the beginning and end points. Then the charging depot data, which is basically the power profile of an existing electric charging station. This is great for validation purposes. And then finally, GPS tracking, which is the best thing that we can use so far, which basically just tells us where the vehicles are at any given point. And then we're able to do our simulations from that. And essentially, the overarching thing here is to know if we took an ICE fleet and made it electric, what would the grid load be? What would the resource requirements be? Which we see here in the simulations. The different configurations we look at can be split up into operator-based or depot-based. So one is more behavioral, the other one's more managed. So if we look at home charging and battery swapping, these are things that operators can do. It's a decision that they can make, also coupled partially with the business model of the provider. But then also looking at solar offsetting and off-peak balancing. And this is something that if you had a centralized charging point, you'd be able to manage quite nicely. And we'll look into that a little bit later. So essentially, the crux of the matter is a motorcycle arrives at a swapping station. He exchanges a depleted battery for a charged one. Then all the depleted batteries join a queue and wait to be recharged. Once a battery is recharged, once a charger becomes available, the next battery starts recharging. And then all fully charged batteries are pulled together and wait to be swapped in. And then just a part of the simulation, the grid load is calculated as the sum of all the input powers of the chargers at every minute, accounting for some sort of charger inefficiency. And then throughout the simulation, we just track the size of the fleet, the battery pool size, and the number of chargers just to understand what would be required to meet the demand. And then at the end of the simulations, we get these nice plots. So if you look over here, this is basically the operator-based stuff. So this would be decision-making on the operator side, and this orange line represents a swapping-only approach. So this is when, and this is taken from Nairobi with the motorcycle taxis, the Boda Bodas. And this is if they were to swap only throughout the day. When they got home, they went to bed, they didn't put their battery on charge. And then the next day, when they ran out, they would swap again. If you look at the green line here, this is the grid load. If the entire fleet were to rather put their batteries on charge at night and then try and make it throughout the whole day without swapping. But obviously, that's restrained to whether their motorcycle can actually make it that far throughout the day. So that's why we introduced a third scenario, which is if you were to swap when needed, but also charge overnight and start the next day with a fully charged battery. And that's what you see here in this blue line. So that's on the operator side. But if we were to look at a commercial fleet, for example, in Cape Town, this is data taken from, well, this was based on data taken from a last mile delivery service provider. And if you were to look at this in terms of a fleet that had a centralized charging point, and you were to able to try and schedule the charging in a way that you could, for example, balance it in a way that you could only use off-peak time of use tariffs, this would be something that we would look at. And obviously, this requires a little bit more resources initially. This would require more batteries, possibly more chargers. But in the long term, your operating expenditure will go down because you'll be paying less for electricity. So in this case, we see an unmanaged grid load profile. And in this case, it's the hybrid, so swapping and charging overnight. And this is the profile we see emerge. And obviously, we see quite a large portion in a peak time, and this is not ideal. So we looked at shifting this into an off-peak time, which you see in the purple line, and we'll get into what that means in terms of resources later, but basically the results say that it is possible, it just requires a little bit more resources. And so we did a similar thing for solar following to try and shift, once again, the unmanaged orange line into, in this case, the median solar irradiance profile of Cape Town. And this would be basically what you'd be able to get if you set up a large enough solar setup and be able to use your batteries to squeeze it into that load profile and essentially, theoretically, pay nothing for energy. We know that's not the case though. And basically, off of these simulations, we see that there is an increase in resources that would be required. It happened to be the case for the solar following that there was a decrease in charges. It's not always going to be the case, but we can see that the solar following approach definitely did better than the off-peak balancing in this case. Just another side note, we've looked at batteries, looked at charges now, but before anything, it's essential to look at whether your fleet is already optimized before electrification or anything. We saw in the Cape Town last mile delivery case that they had a fleet of 385, but with just some basic optimization, we could meet demand with 125 motorcycles. And that's before any electrification or anything. So we can see that these fleets are already kind of overinflated. So this is all been about the simulation side, but there's constituents of the simulator that have also been really, really good to just get into and do some research on. So this is a drive cycle that was developed for Nairobi. And a drive cycle basically is just a representative speed profile. In our case, we appended an elevation profile because it is a key factor to energy consumption is the elevation profile. And basically, this was derived from a whole data set of mobility data in Nairobi into a 30-minute stint, which is statistically representative of the larger data set. And we use this to test performance and in a unique operating environment. So another thing we've developed is just using AI and machine learning to predict the energy consumption of trips. And in this case, this was for electric motorcycles, once again, in Nairobi. But this is cool because it allows you to predict the energy consumption based off of just GPS coordinates or GPS data alone. And it's a much better way of doing it than just using the mean, for example. And you can see on this plot here, just the difference in error rates versus just blindly using the mean, a bit more sophisticated. So all of this has been kind of modular up until now, and at the end of it all, it's nice to have something that's quite consolidated. So I've developed a planning platform which allows you to go and mess around with your own configurations, go and see what your fleet needs. And you guys can use the QR code. I don't think I've got time to demonstrate it now, but you're welcome to scan the QR code, take a look at it later. And yeah, it should be simple enough to use. Thank you very much. Okay, cool. Is that it? Okay.
Yeah, so as Heath is walking up, I just want to mention, so this is freely available. You can go and download it, and then you can plan for grid electrification and see what the impact is. And just as a side note, this crazy dude here finished his master's and his PhD in 14 months.
Testing, 1, 2, 3. Okay. Okay. Good morning, everyone. My name is Heath, and I do research on electric motorcycle powertrain modeling. So my work, I'm just gonna hold this here. My work involves powertrain modeling of the Rome Air, an electric motorcycle that is representative of others operating in sub-Saharan Africa. The powertrain of a typical electric motorcycle consists of the battery, a motor controller with an integrated inverter, the motor, and the drivetrain, which include the chain and sprockets, the rear wheel, and the mechanical brakes. Current design methods by local manufacturers typically involve iterative physical prototyping. This involves building a prototype powertrain and testing it on the road to test real-world performance. This data is then analyzed and compared across powertrain configurations to identify the best setup. My work attempts to improve the efficiency of this process by developing a powertrain model that simulates the motorcycle's performance in real-world conditions. Using this model, the parameters of the powertrain components can be changed, allowing different powertrain configurations to be evaluated within minutes, rather than requiring a new physical prototype and road test for each design. Furthermore, to plan for the electrification of mobility in sub-Saharan Africa, electric motorcycle powertrain models are required to assess performance under various driving scenarios. I've developed two powertrain models of the Rome Air, a simple powertrain model and a more intricate digital twin. The simple powertrain model is driven by measured speed, with the tractive force calculated at the rear wheel and calculations flowing from the wheel reel through the motor and inverter efficiency maps and to the battery. This model enables simple and fast simulations and is used to assess the impact of component parameters and riding conditions on energy consumption. The digital twin is driven by throttle and brake signals, which translate to torque requests that drive the bike. This model consists of 4 subsystems: the battery equivalent circuit model, the controller block that emulates the actual bike's control processes, the motor model, and the vehicle dynamics block, which includes the drivetrain parameters and calculates the environmental forces on the bike. This digital twin enables the user to swap out components or change controller settings and test the relative performance of different powertrain configurations for a given drive cycle. The component model parameters were determined through experimental testing of the physical components. Laboratory tests were conducted to derive efficiency maps for the motor and inverter, battery model parameters, motor model parameters, and the drivetrain losses. Additionally, road tests were performed to assess the impact of speed and battery state of charge on regen braking, and to determine the aerodynamic and rolling resistance properties of different rider and bike combinations. For 6 drive cycles generated in Nairobi, Kenya, The simple powertrain model predicted consumption with errors of less than 3% for half the trips and less than 12% for the other half the trips. These larger discrepancies were due to GPS errors and not incorporating component power limits. This model was used to evaluate the impact of component parameters on energy consumption, with the results shown in Figure 8. As can be seen, the sprocket ratio has a greater impact on consumption than wheel size or aerodynamic properties, with higher sprocket ratios reducing consumption by increasing motor speed into the inverter's higher operating region. The model was also used to evaluate the impact of riding conditions on consumption, with the results shown in Figures 9 and 10. Figure 9 shows that consumption dips between 10 and 20 kilometers an hour due to the low efficiency regions of the motor and inverter. Figure 10 compares different riding conditions against reference drive cycles in the city and highway environments. These results show that increased payload from carrying a passenger has a greater impact on energy consumption in urban riding than on highways due to more frequent accelerations. Furthermore, riding in the low drag position reduces consumption more on highways where aerodynamic drag dominates. For 6 drive cycles generated in Sello, South Africa, the digital twin predicted energy consumption with errors less than 3% for 5 of the trips and less than 12% for only 1 of the trips. The 12% error is attributed to the model's inability to track rapid throttle modulations. Despite this limitation, the predicted battery power and motor speed profiles still closely track the measured profiles, as shown in Figure 12. For the simple powertrain model, the results show that it can provide insightful information on the impact of different component parameters and riding conditions on consumption. However, the model's simplicity causes it to be less accurate than the digital twin. The digital twin is far more accurate than the simple powertrain model, as it incorporates controller and motor limits. From a practical standpoint, the high fidelity and modularity of the digital twin enable manufacturers to use it to compare powertrain configurations more efficiently than physical prototyping. Thank you.
Thanks, Heath. Just change something here. Should come up. No. No worries. Just in terms of Heath's model that he presented, that model can be used to do virtual emulation. So you can basically deploy 100 bikes in Nairobi and see what the impact is without spending a cent.
Nice. That was like a bombshell that he just dropped there. I hope you heard that. Good morning, everyone. So I'm Dr. Stefan Lacock. And yeah, I'm like the practical reality of this lab, because I'm the one that has been hit straight through the face by the business world of going electric, especially in South Africa and across Africa. So I don't want to come over a bit too negative, but I'm going to try and give my best impression of what I think is currently going on and what we can do to fix it, and how actually all the research that's being displayed here today and that we have done over the past years really comes to a point where you can practically implement it and make some critical decisions. But before that, the first thing that I need to present to you is that we are trying to improve the safety of commercial motorcycles across Africa. This is a World Bank project funded by the SSATP. We've also, in collaboration with Discovery, I think most people maybe here have that white chip in your car that tells you that you are driving bad every morning when you're on your phone, even if you just open Google Maps. Completely frustrating. But we are partnering with them to create a similar model for motorcycles. It's together with Rome Electric as well as MSI, which is basically a safety training institute in South Africa, MEN, which is a non-profit organization that focuses on motorcycle safety across Africa, as well as the EV Lab. And this partnership together, last night when I was supposed to practice this presentation, I went to watch Spider-Man, so I renamed us to the Savengers to increase motorcycle safety in Africa. But just to give a quick overview, so motorcycles, even though it might not feel like it here in South Africa, we are close to 27 million plus motorcycles across Africa. In Nairobi alone, Tina's mentioned 2 million. We're close to 2.5 now, 3.8 across East Africa, and that's not even together with Uganda and Rwanda. There's been a 17% increase in fatality rates on roads across Africa, whereas the global average decreased by 11%. 9% of that 17% is on 2- and 3-wheelers across Africa. If you drive at 30 kilometers per hour, you should be safe when hitting a car with a motorcycle. Anything above that, you risk dying, sadly. And as you know, the allowable speed that we are allowed to ride in Africa is close to 60 kilometers per hour. And it's proven that if you have the correct helmet where you can increase your safety or your life when you're in an accident by almost 6 times. Hence, the importance of having the right helmet equipment is very, very important. So the point is there's a lot of research about safety and about motorcycle safety across Africa, but how do you implement a behavioral change in motorcycle drivers when they are driving under conditions that forces them to make deliveries, rides, trips, whatever, as fast as they possibly can due to the money they need to make. The quicker they can do a delivery, the quicker they can take their next delivery. Hence, they're making more money per month, but they're putting their lives at risk. So with Discovery, with this tracker, we are able to track them with 15 hertz data. This means we have very accurate data when they're driving through the towns. It's close, good enough data so that our wonderful Halloran here can see if they are skipping stop streets or not. And we're able to track their deceleration, acceleration, if they are weaving, etc. when they are driving the motorcycles. This basically allows us to build a behavioral model onto the drivers. So we're able to track them daily, give them a driver score, as Discovery is currently doing with their cars. But with that feedback, we are able to basically incentivize them to drive better. But now the key question is it the training that improves the safety, or is it the feedback that improves the safety? So we tested this. We had a small pilot cohort of 50 riders that we trained here in Stellenbosch about a month ago. And we basically gave them practical training. As you can see there, there's a Woolish Dash motorcycle driver going through the cones with one hand. Far more difficult than you think. Most of the drivers that arrived for the training actually arrived around the corner there of the training facility with an insane speed. I actually thought a few of them is going to fall from their bikes. I actually think one did, just when he arrived at training. But afterwards, they were really, really confident on their bikes when we completed the training. We look at defense riding, helmet use, junction navigation, emergency braking, post-crash awareness, and then also the data and ethics and the feedback side of things. We are going to scale this training to close to 1,000 motorcycle riders across South Africa or sub-Saharan Africa. But from the cohort, we had 28 riders that we could track. We had 2,495 trips, about 18,700 kilometers, 5 hours worth of driving, and it was 267 bike days. Now, important thing here, contrary to belief, motorcycle drivers don't drive 200 kilometers per day. They average between 60 to 70 kilometers per day. And also on a side note, they actually make more than most researchers if they do a good job. With this, we were able to track a lot of behavioral stuff, and we put driver scores. Halloran built the model. It works well and everything. But what we actually saw, and I think this is the reality check, is that the driver training that we gave was all behavioral. And sadly, what we think happened, we gave them more confidence to drive the motorcycle. And what we saw is that they started skipping more stop streets and cornering more and actually going faster on the roads. So that brings the question, how do you scale this across Africa so that you can actually see a behavioral change in motorcycle riders? Well, that's where the feedback system comes in. We need to be able to track these drivers daily, create a feedback system in which you can actively prompt them what they're doing wrong, how they can fix it, and what the incentive is for them to fix it. Because the reality of the matter is, and what we are going to try and prove as well through this research, is that without an incentive, the retailers and the money side of things will always overrule the safety side of things. And if we don't incentivize them to drive slower and create a more safe environment for themselves, we're going to struggle to see a behavioral change. So with this, We need a lot of drivers. So if you know of drivers, please let me know. I need about 10,000. So that would be great. But we are continuing with this project within hopefully the next year to see if we can have a physical impact on safety. Then some of you might be tired to see the slide. I'm not, because it's insane. But we drove the Rome Air 6,000 kilometers across Africa from Nairobi to Stellenbosch. Here's a link to the documentary. It has over 150,000 views already. Yeah, it would be amazing for you to watch. But I think today I decided to tell you a bit of a different thing about the story, since I've presented this a lot now. So this is for me as well. This is a photo that Dr. Jason actually took in Zambia. And I was reminded by it recently, since we've done work there in Zambia. There's a guy there in the middle with the green and black striped shirt. His name is Booysen. And Booysen that morning told us that he's actually a high school pupil, that he's basically just finished grade 11. But sadly, due to the drought in Zambia 2 years ago, his village couldn't afford his school fees anymore. So he had to come back to his village to start helping them farm again. And we arrived at that village about 1 o'clock the afternoon. This was about 4,000 kilometers in, so we were quite tired. And then Booysen just saw the bike, and out of everyone in the village, he was the only one who was able to speak English. He came rushing to the bike, and he just started spitting facts at me about why electric mobility is the future. And I looked at him and I thought to myself, I'm supposed to show you what it can do for your future. And he just told me, no, he has plans for this. He's going to farm this way with this bike, and he has a mill that he wants to put on the back, etc., etc., etc. And it just kicked in that, motorcycles is not a new thing in Africa. Electric motorcycles is not a new thing, but it creates an opportunity in Africa to actually change the system in a way that the way we build the infrastructure or the supporting structures around electric mobility gives us an opportunity to build a more sustainable future. And not only for urban centers, which I will get into now, but also for rural settings. This is the best episode. I would really, really advise you to go and look at it. Then quickly, local vehicle production. So this is the Rome factory in Kenya. It was about 4 or 5 years ago, I don't know. Tina sent a very young student to the African Conference Summit to present taxi work, and I found myself on a panel with 4 CEOs, some minister of Kenya, and a billionaire from the Netherlands. And clearly I was outweighted. And I remember my introduction, the presenter actually, they wondered if I was at the correct place, but I was there. I was on stage. And then after the discussion, I got actually invited to see a motorcycle factory in Kenya. And I thought to myself, I'm going to enter a Shabin somewhere. It's going to be 2 motorcycles and that's it. And then arrived at this factory, a 30,000 capacity factory in the middle of Nairobi. The only electric motorcycle manufacturer on the continent at this scale. There's about 5,000 electric motorcycles currently driving around in Nairobi. 275 of the components is localized within the factory. This is the motorcycle, as you saw it beneath. Well, I saw it for 6,200 kilometers. It's definitely durable. It has all the quirks, all the features. But I think just for all of us to have a glimpse and to start learning from what's going on in Kenya. We got hit with this article about a week ago, and I'm being spammed by it everywhere. But the Kenya's e-bike boom runs into a battery and charging bottleneck. There's currently 25 electric motorcycle companies in Kenya. Only one of them operates on a home charging model, and all other 24 companies operates on a swapping station model, the one that we are quite used to. The reason for the bottleneck is due to the following stat. When you have a home charging swapping model, you need 0.2 times the batteries within your network to accommodate those drivers. Whereas if you have a swapping model, you need about 2 to 3 times the batteries to accommodate all your drivers. So what Halloran presented just a while ago, he quickly mentioned if you have the investment or the capitalization, he said it very low key. The problem is, however, in the millions of dollars. If you want to build an effective urbanization system with swapping stations, you need a crazy amount of capital to ensure that that system meets the demand of the environment. And not only that, it's a system that will only work in an urbanized environment. And hence we need to start looking at a system that can potentially both accommodate the urbanized setting as well as the rural setting. So This is not the only solution, but it's one of the solutions. The one is for the driver to own the battery, to provide home charging so that they have that solution, take ownership of the battery and take care of that battery. It's through fast charging solutions for motorcycles, which is not that common yet, and as well as to create a swapping hub, not necessarily only for batteries, but also for maintenance, and to make sure that there's a connection between the OEM and the driver to sustain the vehicle for longer periods of time. Then in South Africa, opening Rome in South Africa is hopefully the goal. It has already been done. We should be officially launching in about a month's time. But the biggest issue, compliance homologations, me and Andrew know that quite well. A lot of people here do. But it's been really difficult, and the biggest reason for it is because the motorcycle is made in Africa. I don't have a European mirror sitting on the side. We don't have a European wheel that's on the back. It's made in Africa. But sadly in South Africa, well, not sadly, it's a good thing, don't get me wrong. All our standards are based on the European international standards, which is good if we had the test facilities to actually test these components and these assemblies to make sure that they are compliant to those standards. But to expect startups to invest and take a vehicle back to Europe, get it tested and certified and back into South Africa, it's just not realistic. And I think there's a hard look that needs to take place in terms of compliance and homologation and how we're going to test this. Investment and finance, money is always the problem. Registration and licensing, there's a chicken and egg situation. In order to manufacture a vehicle in South Africa, you need to be registered for VAT. In order to be registered for VAT, you need to sell a vehicle in South Africa. In order to sell a vehicle in South Africa, you have to manufacture a vehicle in South Africa. Sadly to say, you need one of those three to happen somehow at the same time. I'll let you know when I get it done. And then finally, testing, pilot, and execution. Just to test these vehicles has been an immense challenge. I think most of the lab's resources actually goes into how to figure out to get a vehicle onto a road to safely test them. And without testing and piloting, the normal South African doesn't trust you and doesn't want your product and doesn't want your research until you've proven it on the road. And I think there's also a clear opportunity for us here to create something that we can accurately test vehicles in safe environments so that we can prove it on the local scale. So if we want this, 24,000 direct and indirect jobs through a 30,000 capacity electric motorcycle facility, we need to start going in the right direction. And this is me about 2 years ago preempting that I'm going to watch Spider-Man before this presentation. You can see I have a grimace on my face. It's because my back was in pain, and I can honestly say my back is still in pain. And it's been a tough journey, but hopefully through the research that we're doing here and everyone that's listening to me now and hopefully is going to come and provide me some assistance afterwards, we can move forward and create this and make this a reality. So the opportunity, Spider-Man finished off last night. He told MJ that we can't do this alone. And I want to tell you today as well that we can't do this alone. Thank you.
Thank you, Stefan. An important thing that Stefan mentioned there that you may want to just think about is it makes sense to do home charging. But to do home charging, especially in the townships, we need serious electrical infrastructure investment. So we're switching gear now to minibus taxis, and you'll see a lot of the stuff that Joshua presents from the minibus taxi perspective tell the same story.
Thank you. Hi, everyone. My name is Joshua Sello. I'm a researcher here at the Electric Mobility Lab. And thank you to everyone who's come and to speak. I'm going to speak exactly like what Tina said about the electric minibus taxi transition and how we plan for that and how we simulate and the work that has been done up to this point to get us there. And so just to give you guys some context, this is the work that we're kind of doing. We're trying to understand the system that is minibus taxis and then what the impacts would be if we were to electrify them. As we know, these are not very organized not organized, but very static and very predictable systems. Minibus taxis typically follow demand where they see it. They typically operate on their own schedules and they are very decentralized. There's no one major organization coordinating their operations and so on. So you have various components like the vehicle that you need to understand. How do these vehicles operate within real world systems? What the performance is and so on. And then you have the driver, the internal driver behavior and what makes drivers move from point A to point B, what are the incentives behind that, and so on. And then influencing that behavior obviously is the passengers. This is the main source of revenue and profit for these drivers and the owners and the organization structure. And then you have the way these drivers and vehicles operate on the infrastructure. And so, oh, sorry, thank you. Yeah, so then when you actually look at then what happens when you electrify these things, it's not a simple engine swap. It's not simply saying, okay, let's make everything electric, as you'll see a bit later on in my presentation. You have to really consider what happens to the driver's internal model when they have to consider how do I balance servicing demand and then also charging. Charging has a massive knock-on effect on what the operations look like for these drivers. And so we have to be able to predict that in order to create a hospitable environment that these vehicles can operate in. So added onto the sort of effects that will impact these drivers, you also have infrastructural impacts. You'll have to install charging stations, deciding what the correct amount of charging points to put at each charging station, the location, the power output are also very important. And then you also need to consider the limited, what's mentioned a lot before, is the limited grid capacity at these locations. These need to be accounted for before you start planning and rolling out very expensive equipment to these places. And then also there's differences in the vehicle, the way energy is used to convert that into locomotion. For example, you have fuel and petrol and diesel in ICE vehicles or internal combustion engine vehicles. And then for electric vehicles, you will have electricity, whether that comes in the form of AC electricity converting to DC, or you have directly DC or high power DC electricity, and so on. And so just to start us off, the first sort of, or a good basis to start off to understand the impacts of electrification or moving a vehicle into electric locomotion is to understand what the actual real-world performance will be for minibus taxis that are operating on South African roads. As you buy a vehicle and so on, you'll have a catalog efficiency that the manufacturer, the OEM, says that this is how you can expect the range to perform in very nice tested environments. But when you actually deploy these, you actually don't know really what the performance will look like. And so with the help of Dr. Lacock and Chris and so on, we actually, also with the help of Cometro and FlixEV, this is the Ikamva vehicle that was imported to be the first pilot of electric minibus taxis in South Africa. If I'm not mistaken, it will be actually operational around October. And this vehicle was first, before it's now deployed, we tested or got measurements from the vehicle using telemetry data and then converted that or created a model to then simulate or essentially predict what the efficiency would be for various driving conditions. And after doing that and then applying that to a standard WLTC test to get a sort of expected performance, we found that, for example, when there's unloaded flat conditions, you have about 0.28 kilowatts per meter, so essentially how much energy per distance this vehicle is going to use up. And this has a massive knock-on effect for range, for energy requirements, for costing, for operating costs, and also for our downstream modeling, because now this provides a very stable input for these models to then be able to estimate other knock-on effects like infrastructure requirements and so on. Also there, with loaded flat conditions, we found that you get 0.33. So a good rule of thumb is also, you can just divide by 3 and say, okay, if I have this much distance, for example, I want to cover, I can then divide that by 3, and this is how much energy I'll be using. So that was kind of the empirical sort of measurement we got. And next on that was, and what Halloran also very touched on very well, was that we have, we need data. We need data to actually be able to plan and organize and figure out which directions to go into if you want to figure out what the best solutions for infrastructure requirements and deployments are. And so we had various, that one's a bit skewed, but it's fine. We had various data sets that we were able to use on. These are data sets from real world taxi drivers operating continuously throughout the day and so on. And previously we had fairly limited data. Notoriously, the industry is fairly opaque. It's very difficult to actually get data, but we managed through amazing partners that we managed to actually get quite a lot of data on a plethora of different minibus taxis throughout the country. Mainly shown here are Western Cape, where we had the Blue Dot data set, giving a bulk of the information that I used in my models. And then we have in Gauteng, a company called Sebenza provided a lot of data. They have countrywide data set, but they have data on, for example, about 7,000 minibus taxis operating currently. And this was very useful, for example, getting the baseline understanding on how long do these systems operate on a daily basis? How does this shift, for example, from a Monday to Tuesday, or from a public holiday or holiday, festive season to an everyday operation? And then you also can look at when do they start their day, when do they end their day, and so on, to kind of also figure out where the opportunities are for charging windows and so on. And next, after getting, obviously, analyzing the data, an important aspect to also understanding sorry, my mouth is getting a bit dry. Yeah, to understanding electrification is understanding the baseline static viability, and amazing work has been done by people like Chris or Dr. Abraham, Dr. Pretorius, Brendan. He did a lot of good work on understanding the grid impacts of taking the static or the current mobility of these vehicles and assuming that they are electric, and then seeing what the sort of charging opportunities will be, what the grid impact will be, the power draw, and so on. And that was then sort of static. So this resulted in one of our Tina showed before, an amazing publication in Nature, where we were able to assess this on a large scale in Cape Town and see what the benefits of electrification, where the bottlenecks are, and so on. And the key takeaways from these plots, I would say, would be that viability increases when you place the infrastructure close to where these drivers are. So, for example, if you place the infrastructure at sort of more what you consider informal stops, at more informal depots and so on, this had a massive benefit to viability because the vehicles are stopping there anyway. You might as well move the infrastructure there. Obviously, this comes with a caveat that you actually can't. These locations are notoriously underdeveloped in terms of infrastructure and so on. So there's a big need to actually invest in this, and you'll also find obviously knock-on effects of having better electricity provision for the people that are already there. Another insight was that the viability does change depending on which group you are, or notoriously, thank you, which group you are previously on. Thank you so much. Much better. Okay, yeah. So the viability changes, for example, the grouping your racial classification under the census data. For example, if you're Black African, your viability, because of where you are in the mobility, you find, for example, Black taxis have to travel a lot further in a day than you find for colored taxis and so on. So the viability shifts. And so that is an important consideration. You need to make sure that this transition is equitable amongst different racial groups and so on, so that you're not benefiting one while disadvantaging the other. And then another insight is that, for example, you might not need to overspec your system. You might not need to have 50 kilowatts massive power if the vehicles are already stopping for long enough that they were able to get there enough energy for the day under a lower 22 kilowatts AC. That should be perfectly fine. And so after assessing the baseline feasibility, my work came in where I'm trying to understand the behavioral implications of electrification. And through this, I use what's called an agent-based model. And essentially, as I mentioned before, minibus taxis they have a lot of agency. They are able to make their own decisions on their scheduling, their routing, and so on. We can look at the data to inform how that looks on the aggregate, but there isn't a sort of head-fast rule that says minibus taxis will leave their house at 4 o'clock and they will come back home at 8 o'clock, and these are their schedules and so on. So we need to be able to work with that sort of randomness and that agency and build that into our model so that we can better plan for that. And so this is a little animation of the model that I developed to kind of show how they actually look at. And you will see on the right, or the right panel, you can see in a simulated day, this is an example. I can run, for example, hundreds of these simulated days or thousands of these days, and then see on aggregate what the sort of probability of a failure of a charging station or a vehicle might be if we do this enough times. But you can see, for example, for one day, hopefully this does display. So it's still obviously in the midnight, nothing's happening. All the taxis are sleeping, the simulated taxis, and eventually they will decide, okay, I need to go and make money. And that happens around 4. You'll see the first couple of taxis. Hopefully you can see those arrows. The green ones are the electric ones, and then the blue ones will be the ICE ones. And as they go out, they might decide to charge. Once they've for example, manage the massive bulk of peak morning traffic or peak morning passenger demand. They will decide, okay, I need to charge now. This is the best opportunity to charge. And so balancing charging opportunity and service delivery is a massive challenge in this kind of model. So how do you actually assess that and incorporate that into your model so you can get accurate results? You can kind of see this is one day now they've done, and some are going home, and you can see, for example, they managed to service most of the demand in the morning and the afternoon, coming from, for example, Stellenbosch Central in the morning, going to Stellenbosch Central in the morning, and then coming back from Stellenbosch in the morning, in the afternoon, sorry. Yeah. And then what's nice about these kinds of models, as opposed to the previous sort of study that assessed this baseline feasibility, is that you can actually now assess what's the impacts of electrification on service delivery, on passenger, for example, passenger request or how many passengers, for example, were picked up in a timely manner, what the effects on wait times will be, what the effects also on the driver's side, what is their average occupancy, and so on. And so from these plots, it's a lot, but the key insight, I guess, for the vehicle utilization is that you'll see that increasing adoption or for constrained infrastructure needs will increase utilization, but that's because that these drivers aren't able to move. They don't have enough power to actually go and get out. So they're off more full most of the time, but that's because the entire system is constrained and so on. So with these kinds of systems, you have to look at each component and how they relate. So as, for example, tip service, the percentage of tips that are being serviced goes down, they're getting more utilized and so on. And that is something you have to take account for when you're looking at these systems. Additionally, you can see also that when you increase the infrastructure requirements, it does increase the cost, but then it will also increase service reliability for the network or for the transportation system. And you can also see at the bottom, the purple plots, it's lighter the more power you add into the system or the more power you provide to these taxis. But essentially, that's how constrained the wait times are throughout the day. So there's massive wait time a bit before the morning peak, and then the peak of the wait time is in the middle where there's no passengers ready to service. So most of the taxis decide, okay, I'm going to go charge because I might as well. There's no one really to go and pick up. And then there's a bit of a peak just before they go home to get a bit more energy for the next day. And then on the far right, there's a plot just to kind of show what is the system or the simulation can be used for, is that they can be used for optimization. For example, figuring out you can ask yourself sort of counterfactual questions, like what is the best or the most ideal taxi or number of seats that taxis should have to better suit electrification and so on, because electrification gives us the opportunity to actually rethink maybe mobility and so on. So for example, I tested for that, but I can also test or detest for the best amount of charging, number of chargers, the best location, the best power output for these, and fed these into us optimization algorithms to then spit out what the best, which designs. But again, it's not the best design. It would be trade-offs between different components. A bigger vehicle, for example, can be, for example, if it's a bit small, but bigger vehicles use less energy because they can carry more passengers to meet the same demand. But for example, they're less flexible. You might get less service delivery out of them, and so on. So you can find, for example, in this case, you have 35 seaters, which are the orange. You have green, which is 15 seaters, and then blue are the 22 seaters. And the arrows represent which metrics you're assessing for. For example, unserviced demand, passenger wait times, charging queue times, costs, and then you also have peak load and total costs and so on the right or in the second quadrant. And you can see that 22 seaters kind of balance all of them, where they will have lower costs than the 35 seaters, but higher cost than the 15 seaters. But they also don't produce as much load. They won't use as much daily energy and so on. So you can balance all of these factors and assess without having to do expensive pilot programs to then see what will happen. And then lastly, I just want to speak on a very important aspect of electrification, which is the environmental impact. Tinus mentioned very early on that, yes, electrification is important in terms of the long run environmental and sustainability goals we have. But then at the current moment, the carbon intensity of South Africa's grid, if these vehicles are charging off the grid directly, won't really see that sort of benefit. So an important aspect in the immediate term is that these vehicles will be clean in terms of particulate matter emissions, so PM. You can see that electric vehicles are a lot less, but currently they are on par in terms of carbon dioxide emissions with petrol and even more than diesel because of the carbon intensity of the grid. So we actually do need to be very serious about how we deploy utility scale renewables, or at depot level deploy solar charging, at least to offset and make these vehicles a lot more greener. Again, this is a result from the agent-based model where you can see that as adoption increased, the emissions also increased because the more electricity was being used from the grid, and that will cause that a knock-on effect of more emissions being used. Thank you. That's all from me.
Now we're switching gears again to buses, and we have the fortune of a Golden Arrow bus employee who's actually doing all their data analytics, doing a master's here. So this is Luqmaan. Good luck.
Thanks, Dennis. Everyone can hear me? Good morning, everyone. I'm Luqmaan Ryklief. We'll be presenting work doing the analysis of the data that we have available at Golden Arrow for our electric vehicle fleet. Obviously, Golden Arrow is one of the places on the continent with the unique amount of buses that you might not find anywhere else in close proximity. And this is obviously an operation that we would like to copy and paste throughout the city, the province, the country, and the continent as well. And before you can decide what this configuration looks like, you start asking yourself various questions. How many buses do we buy? How many chargers do we buy? How big are the batteries of the chargers? Is our grid connection for that infrastructure enough? And if you get that number wrong, one of those, the decisions that we make further along the line becomes harder and harder to reverse. Yeah. So we start with, obviously, getting that number means starting from good data. And that's harder. It's harder to find than it looks, because every bus reports on itself constantly. Every trip is logged, and every charger is reporting how much energy it's dispensed. Right? None of that's useful on its own. The work is in stitching all of this together. Here I've gotten a perfect example of 4 different fragmented systems: CAN bus, GPS, actual schedules and trip allocations, and then the charging data itself. The work is in stitching them all together so that we can tell one coherent story that this bus went on this trip, it had this efficiency, it arrived back with this state of charge, it charged at this charger, and this is the amount of power that we delivered back into the bus for it to go see its next trip. And so obviously, now that we have built our data foundation, as Halloran demonstrated, we can now start building digital twins. And in this case, the digital twin is a simulation of the bus and the depot that we can experiment on. Because we would want to know what happens if we double the amount of buses, or if we halve the amount of chargers, or if we need to increase our grid capacity, or do we need solar? Do we need on-site batteries, right? And having a digital twin or a simulation allows us to perform those experiments, not on the real infrastructure and not with real money. So as shown previously, the digital twins allow us to do a plethora of real-time optimization and analytics exercises that encompasses a wide array of systems. To monitor fleet characteristics such as the state of health of the batteries, and actually tracking the SOCs of the batteries live, whether they are in the depot or whether they are on the road. And we can also do fleet statistics such as the consumption and whether to know whether the vehicles need to be in service or not. The diagram above shows obviously the different avenues that can be taken with having different digital twins and different digital twin simulations. And the two that I'll be focusing on is machine learning and the data collection. So this graph looks like a lot, but what it is essentially it's nearly 600 trips from the real fleet. And the simplest possible approach, which is the one that we use in the industry, is the one average energy figure that is applied to every bus. It's applied to every route, right? And if that were good enough, a lot of these dots would be a lot closer together, but they don't. Some trips almost use double the amount of energy as others. Same bus, same route, and yet there is a different reality on the road. A flat number or a flat average can't see any of this. So we asked the data, what is it that is driving this differentiation in consumption? And the bus departs and returns to the same place, at least at the case with Golden Arrow. It departs and returns to the same place, so the net incline should be 0. So it shouldn't really have an effect, right? Well, when we ask the data, in this exercise, we use the machine learning to rank every possible feature. I'm sure there are more, but every plausible feature that would matter, and by how much it would matter. Hills, route security, distance, road type, time of day, temperature, all things that affect the consumption of an electric vehicle, and essentially the cost drivers of the performance of the fleet, right? And the answer surprised us, as we can see here, that it wasn't geography that had the biggest impact on the consumption of the electric vehicles. It was the conditions themselves that the buses needed to operate, right? It's barely the route at all. What matters most is when the bus leaves and how cold it is outside, right? That's the insight that a flat average might not, was always going to miss. And it's not that the buses are unpredictable. It's that the thing driving them is not geography, but conditions. So here I've got an error bias across the day that actually assesses what we do or how the fleet would perform if you use a model or a simulated model versus using the fleet average, right? And each box here is the spread of prediction errors for the trips during the morning, during the daytime, and during the PM peak, right? Sitting close to 0 means you're getting it right. For example, here, and going either side means that you're getting it systematically wrong in one direction. Not once, but every day, okay? And not just on a bad day. So the flat rate approach here underestimates the morning peak by 4%, right? And that's the one window where underestimating is genuinely dangerous, because the morning peak has to have adequate charge and it has to leave early. And so if your planning number is too low there, right, you're quietly under provisioning exactly the amount of energy that the charging overnight requires, right? And that determines whether every bus can make it out for the morning peak. Then in the afternoon, it swings the other way around, actually. As we can see here, in the afternoon, it actually overestimates between 6 and 7%, which sounds safer, but it means that capital gets spent on charges and on grid connections that actually isn't needed in that period of time. So you can't fix this with a single correction or a correction factor either, because the error isn't constant. Like I said, it flips in directions across the day, every day. You need the full-time varying picture, which is what the model gives you, and the flat number never can. And this is probably the biggest takeaway from this exercise. And this is the same story translated into something an operator actually plans against, right? How much energy is each bus returning to, and when is that bus returning? Hour by hour, we can see here across the whole depot. You can see the shape of the day essentially in the chart, and you can see when the depot peaks in terms of electricity, and that actually gives you the amount or projects the amount of electricity that is required, which is a direct cost driver for infrastructure planning. Looking closely at the model, the blue, which is the model, tracks the reality much more closely compared to which is the black bars across every single hour. And the flat rate, or the orange bars, you can see it underestimates during the AM peak, and it overestimates here during the afternoon peak. So there is a very good example of the drift that one sees, and it's not just across the entire fleet, but it's across the entire day as well, and that's every day. And for buses operating 365 days a year, those costs can stack up pretty quickly. So you put both parts together, and the message is simple. If you get this number wrong, and you get the wrong battery, and you get the wrong number of charges, and you get the wrong grid connection size, it's a real capital size of the wrong curve at the exact moment that the depot can least afford it. And that's the piece, essentially. That is the piece that we've built and proven that works. This is part of a larger research operation, where this is just to calculate the energy of the fleet. Next, beyond that, would be integrating it with chargers, integrating it with solar and batteries as well, so that we can run these experimentations on different scenarios. Like I said, number of buses, number of chargers, what are the power requirements, and so that we can run these simulations not on a real infrastructure and not using real money. Thank you.
Morning, everyone. Can everyone hear me? Okay, cool. So, fun fact, 2 years ago, mobility day like this, I was sitting down just like everyone else, and Tinos was presenting, and everyone else was presenting, and I was like, nope, I need to do my master's under him. And here I am presenting also. So, cool. So I would also talk about electric buses, and because I've been in the industry for a bit, I was also intrigued by major things that were going on. And I was also working on data that Manu was also giving us, and thanks to you too. So yeah, what if all buses could be electric vehicles? Like, I do get this at work. Everyone tells me, maybe we should get an electric vehicle. And probably some of us here do have an electric vehicle. But it's like, yeah, let's get an electric vehicle. Let's get a bus. And look at it, this is golden arrow. It looks very beautiful. Like, this is all electric. But the issue is, there are some problems we're probably not seeing. And it's like, yeah, the pros of getting an electric vehicle is, maybe the problem is, first of all, the problem of an electric vehicle is it's very expensive. And probably that's the only reason why people tell you, like, you should not get an electric vehicle. But there's so many pros, right? They'll tell you, one, it's less on fall, less energy cost, meaning you can just charge at night or charge at home, and you don't pay for diesel to fuel the car. Very low on maintenance cost. There's no pipeline, no tailpipe emission, and it's cleaner, quieter. There's few moving parts. It's more energy efficient, etc. Right? That guy said yes, absolutely. We should get an electric vehicle. So I'm talking in the part of an industry-minded person, yeah, where we're in a meeting and everyone thinks we should get an electric vehicle, and that is what my boss is saying. Yeah, let's get an electric vehicle. But there's a problem that no one is talking about. And that's where my research came into, because we needed to figure out what is the negative coming out of the good thing we're trying to solve, right? And the problem was the charging problem. So that is a big thing. So one big thing I picked out of university, coming out of undergrad and going into the industry, was looking at big complaints, electricity bill. Like, there's a thing there that's called demand charge. And if you go above a specific NMD, which is notified maximum demand, ESCOM or your municipality charges you a particular penalty fee. That is very expensive. So that is even exclusive of what you actually consume from the grid. And also there's something called demand charge, which is your highest KVA that you ever pull in the month, right? And Eskom charges you at a very specific rate for that. So demand charge is a problem. Charging problem is a problem here. So what happens in the case of Golden Arrow, using for an example, is all vehicles arrives, and the question is like, when should we start charging? So first time is like, let's just charge when we arrive. So all the buses are being charged when they arrive. And we noticed that maybe we're charging during the peak period. Electricity is very expensive in the afternoon or in the evening compared to at night, because that's off-peak period. And then the idea was like, okay, you know what, let's just stop charging. All the vehicles arrive and let's start charging at night, 10 p.m., because electricity is cheaper. But then, should we charge all the vehicles at the same time, or should we just stagger them? We don't know. So, but we need the vehicles to be available for the next day, 4 a.m. or 5 a.m., so they can go for their full ride. So now the question is, let's just charge everything, since we're already using cheaper electricity. But then, your consumption value, what you pay to Eskom in terms of consumption, in terms of kilowatt hour, megawatt hour, is low, but also your demand charge is so high because all the vehicles are charging at the same time. Now that brings in some grid capacity. So this is what happens here. The vehicles arrive, the demand charge spikes up because you go above your demand charge, and you pay so much for that, even though you're using an electric vehicle, and even though you're charging at night. Now it's putting some strain on the grid and also some strain on your capacity. So what is meant to be a solution for us for getting an electric vehicle, paying less on energy, is not a problem because we're paying so much because we have an electric vehicle. And that's where my research came into, right? So the first step, okay, it's a lot probably. So in my research, what I thought about was, excuse me. So what my research thought about was this. What if we could build an optimization model? Just simple, just get it like a mini computer. What it does, it takes in all the data, the vehicles arrival time, the SOC, the amount of time needed for the vehicle to be at the depot, for it to be charged before the next period. And so what it does, it takes all those time, takes all those data, and once the vehicle arrives by maybe like 5 p.m., whatever time it arrives, they all wait till 10 p.m. at night, and it staggers the charging. So what it does is like, it calculates based on the SOC it arrives. So if a vehicle arrives at 60%, or another SOC arrives at 30%, a 60% vehicle just needs 40% to charge, and you could charge it for a shorter period, or you could charge for a longer period with a very low kilowatt. So instead of giving the same capacity demand or demand charge capacity to each vehicle at the same time, you stagger it. So it measures based on what is needed for each vehicle. And that is the nutshell of what my research was. And instead of them paying so much on their demand charge, we could bring down their demand charge by 17%, which is like the essence of getting an electric vehicle, because you actually want to pay less on electricity and also utilize the energy efficient from the vehicle. So we brought down the demand charge by 17%, and we kept in the case of Golden Arrow, we tested with 50 buses, for example, at this stage, because there's only 50 buses that are available at Golden Arrow at the point, and we needed to stay below their NMD, the notified maximum demand. And we charged with stagger charge, and we brought it down to less than 1 megawatt, I mean. And then all the buses were ready by 4 a.m. for the available dispatch. So thank you, that's my research.
Just to be sure, we simulated. We didn't actually.
Yes.
They got there before we did, so we got up with an answer and we said, hey, it's 27 kilowatt. And Gideon said, yeah, we've been doing it for a week or two. So they were there before we came up with the answer. Now we're shifting again. This is actually a final year student. We're hoping to get him onto a master's project next year, presenting on electric scooters.
Morning. My name is Ben. As Mr. Booysen said, I'm a final year mechatronics student currently doing my scriptsy, which involves developing a digital twin for an electric scooter. Digital twin is essentially a working copy of the exact scooter, behaving in the exact same way so that we are able to run tests on it without needing the physical scooter. I built the model using real measurements taken off the real scooter, and I'm currently testing it with real rides around Stellenbosch. That's what I'll be walking you through today, what it's found, why it's important, and what it's telling us. Fittingly, this is the smallest vehicle on today's program, and maybe the one with the most to prove. Here's why it's worth taking a look at. Scooters can generally be a cheap option to transport people around our city on short trips. It's cheaper than a taxi, it's faster than walking, and no license is needed. Picture this: campus students, a delivery driver, anyone looking to do a 5-kilometer hop. Too far to walk, but too short to justify a car. Here's the catch: nobody knows if the sums actually work here, because every value assigned to a scooter has been measured somewhere else. Different climate, different roads, different traffic. So I measured it myself. Every part, the battery, the charger, the motor, the drivetrain, all taken off the scooter, put onto the test bench, down to the motor and the controller that show peak efficiency of just above 78% at around 25 kilometers an hour. What comes out the other end is essentially a working copy of the scooter itself, behaving exactly the way the real scooter behaves, not the way the textbook says it should. This kind of information is worth knowing for more than just this one scooter. Right now, anyone planning to invest in a fleet or build infrastructure around one is currently working with borrowed numbers and a bit of hope. And getting it wrong means real money spent on the wrong bet. No model like this for a scooter has been built under African conditions before, and therefore the results I'll share with you today are not borrowed from anywhere. They are the first real results we have to whether this will work here. Once you start measuring and stop assuming, there are certainly a few things that turn up that nobody would expect. Here's one that surprised me the most: regenerative braking. That free energy you're supposed to get back every time you brake recovers at 76% above 15 kilometers an hour. So yeah, it recovers 76% above 15 kilometers an hour. But as soon as you drop below about 10, exactly the speed at which stop-start city traffic takes place, and it barely works at all, sometimes consuming even more energy than we are getting back. Therefore, anyone planning to size a battery or daily range for these scooters cannot rely on this free energy coming back, not in our traffic, especially because this is where most of these scooters will be operating within the city. It's the same story when looking at the charging and the battery itself. Two more things worth noting, and both change what you would actually budget for. First, how you charge it matters. A full charge runs at 87% efficiency, and a quick daily top-up runs at 82%. Therefore, a fleet that is constantly topping up is silently paying more per kilometer than one that is charging fully less often. Combining all these numbers together, it comes out at about 7 cents per kilometer for the scooter to run. Secondly, the label lies a little. This pack is supposed to be getting 6 amp hours, but we are actually only getting about 5.3 of those, and that shrinks further the harder you ride it. This might not seem like much, but multiply this across a fleet's range promises, and this is the difference between a scooter that makes it home and one that doesn't. Two small gaps on paper, but exactly the type of metric that ruin a fleet's numbers if not checked out. So I'm busy checking it out properly, out where it actually matters, and not just once. So far, I've done 4 rides, over an hour of real riding, about 19 kilometers in total, on different routes, different terrains, both steep climbs and flat cruises as well. Every ride's worth of data holds together too. I built a way to line up the GPS, the altitude, and the scooter's own onboard readings. And by the end of the ride, they agree to where you are to within half a meter. This level of testing brings up real problems, which is exactly what you wanted to do. So far, I found and fixed 3 bugs within the model, and since that's been sorted, the prediction error has dropped by roughly 2/3, where we are getting energy prediction errors between 0 and 5%. Chasing down those bugs has turned up something even bigger, a genuine, recognizable limitation in how these models are normally built, the kind of limitation that is noted down in research but is yet to be solved. This gives the next phase of my project a clear and concrete direction and not to just do more testing. Though, with that said, this is no longer a guess, it's a tool. Anyone looking to buy or invest in a fleet of scooters now has real answers to do with range and running costs. And anyone before having to spend a rand, not after, and anyone planning to build the next one of these now has real numbers to work on when sizing the battery or the motor. This is exactly the type of work we are trying to do here, to stop importing assumptions from somewhere else and start measuring what's actually true here in our climate, on our roads, with our traffic. And for scooters, I just think the sums might actually hold up. Thank you.
Thanks, Ben. So Ben is supervised actually by Dr. Stefan Botha here, and the next person is also not supervised by me. It's supervised by Hubert van Eden, Professor. Talitha speaking about freight. I just wanted to say one more thing. Oh yes, I love this. This is actually what you could call our students as well. When they arrive, it's a big guess, and then when they finish, they're a tool, right?
Good morning, everyone. I'm going to shift the conversation a bit to the electrification of freight transport. So I'm going to talk a bit about some of the findings that came from my master's and then directing it a bit more to where my focus is now for my PhD. So when thinking of electrification for freight transport, it's important to think about it in the perspective of the integrated feasibility elements, which is from an operational, financial, and technological perspective. So not just purely whether it can work in your operations, but also does it actually make financially sense. So one of the key aspects from my master's is to take real-world operations and turn that into the energy and operational demand and understanding how these vehicles are being implemented within current operations. So like you can see, the trip information informs operational and charging demand, which then informs your technology in the terms of your charging infrastructure requirement, your planning towards energy management, as well as what size battery you're actually required to have. For the study, some vehicle movement was analyzed, so using only trip level information from a single vehicle, and understanding the patterns for vehicles that are feasible, possibly feasible, and then not feasible. From this, it was found that it's not necessary to just look at your vehicle. You have to actually look at your schedules, the time constraints within logistics. These play a major role and add to the complexity of actually electrifying a fleet. All of these aspects actually have a financial impact and are under strict service level agreements, which add an extra complexity since you have to meet your customer demand. So when looking at a holistic implementation, all these elements have an impact on one another when making decisions to implement the technology. One of the main findings that was found from the study was by doing a financial analysis, looking at company financial data, and then getting to a key metric for cost per kilometer. And one of the key aspects when looking at operations is whether a vehicle is actually doing enough kilometers to justify investment to have electric trucks instead of the current diesel vehicles. So like you can see, daily distance had the highest sensitivity value. And when you fluctuate the cost by plus minus 25%, if your vehicle is not doing enough distance, it just doesn't justify the investment for a company, since that is one of the main driving factors to implementing, especially when it comes to logistics. Another key aspect that came from the study was that when implementing charging infrastructure or a larger vehicle capacity to ensure that you actually are able to meet all your operations based on the size of battery, the charging infrastructure actually plays a minor role in the implementation cost. So meaning that when you have a larger battery, you're paying more, but if you have more charging opportunities, you can actually have a smaller battery size and make the cost less and the financial burden less on a company to implement the vehicle. So from this, what does it mean? For my PhD study, I'm looking at specifically the smaller operators, companies who can't afford the investment or the big financial burden, companies owning about 1 to 5 vehicles, and playing with that trade of adding more charging infrastructure or more charging opportunities rather than having a large oversized battery. So the idea is to have collaborative opportunities for charging, companies working together to implement charging infrastructure so that the financial burden can be split across various companies and have a collaborative opportunity to charge. With this, there comes another complexity, which is the time slot allocation for charging and strict time windows that companies have to adhere to, but this also increases the utilization of the vehicles while they are standing. So one of the findings was also that most of the time the vehicles aren't driving and they are standing either loading or unloading or standing overnight waiting to make their deliveries. So this is where the solution is working towards using telematics data to kind of analyze where these opportunities might lie. And that all plays for the plays towards the trade-off between having a larger battery or implementing more charging opportunities to ensure that you have financial feasibility. Yeah, thank you.
All right. As you make your way to your seats, let me quickly introduce Waldo. So we're moving away now from technical research and we're heading into skills development and looking at the part of our projects that's funded predominantly by TETA. So Oma, thank you very much for coming. Oma is she's our research manager. Did I get that right? Yes, research manager at TETA. And they've been an incredible lifeline to us. And to be honest, we signed up for that project because we had to get funding, but it turned out to be an amazing opportunity for us to really think carefully about the skills that are required, and it's enabled us to build the capacity to do training. So as I said last week and this week, we've been training at the City of Cape Town, and we're also going to provide more training as part of that project. So they've coincidentally, they forced us into a position where we're actually very happy. And now Waldo is going to demonstrate something that seems technical, but the whole idea here is to transfer knowledge of electric vehicles. Then Dr. Chris Abram is going to take over, and he's going to present some of the research that we've done through contacting you guys and asking what skills are required, industry partners, etc. And then we'll take it from there. Thanks, Waldo.
Is that fine? Cool. Okay. Hi, everyone. Yeah, I heard the question before break was, where was Waldo? Here I am. So, yeah. As Tina's briefly introduced, this project of ours, the vehicle on the bench, EV wall, as we did call it sometime, was commissioned by TETA. And in essence, what it is, if you see on the slide here, it's the Rome motorcycle Stefan introduced to you deconstructed. It's 90%, 95% of all the components on this is from the Rome. They sponsored some of the components to us. And we basically put it on a wall for educational purposes to understand how electric vehicle works. So I'm going to go in slight technical stuff about how electric vehicle works, not too deep, because I know there's a lot of technical people here, some not. I'm just going to touch upon that, about just core principles of an electric vehicle. And then I'm going to show you a quick demonstration of what we actually built here. So just on your left side, you will see we've got the wheel, which is basically then connected to the motor. But let's start at the battery. So at the back, you can't see it on this image properly. At the back there, you could see here, we've got our batteries. That houses our energy that you would have in an ICE engine as your petrol. So that houses our energy, the DC part of our energy. And then that gets fed up to our inverter here through the DC line. This inverter then transfers the energy to three-phase, which gets fed to our motor. So the three important stuff is you've got your battery, you've got your inverter, and you've got your motor. That is the core principles of how electric vehicle gets driven. So this three-phase then gets fed into the motor, and then that energy gets converted through magnetics and stuff, and the motor drives. Some other core components also is we've got a DC to DC converter there that just takes the high voltage down to 12 voltage, which basically does all the auxiliary peripherals, the lights, the flickers, the tutor, your speedometer, etc. That powers that because that doesn't run from the high voltage side. Anything else on that side? Oh, and then very important, so for this bench, that was the core principles of our vehicle works. On this bench, we've got a second motor, very important. So at the back, you'll see we've got a second motor. That is what we call the environmental motor. The front one is the drive motor, that is the actual vehicle which we are driven. And then the environmental motor at the back is just another motor that we can use to simulate our environment. We can use to basically add some load to this vehicle so that we can see the current spikes, see the waveforms, etc. That also gets driven from a battery with its own inverter, and then it is hard coupled in the middle, the two attached to each other. And that's the core working principle of this bench. Then this enables us to do a lot of simulations. Basically, sort of, it wasn't the sole purpose of it, but later on we realized this is sort of a dynamometer we built here, and we can do a lot of just normal simulations, regenerative patterns, drag situations. Yeah, so this is a GUI we built for us as engineers. This was actually the first version we built, and then Dennis came to me and said, Waldo, a lot of people don't know what's happening here, so let's tone it down a bit. And then we built one which is just showing some core GUIs in terms of your torque, your power, and your speed with the throttle. And then the one I have here today for you is a third version, which also basically we have on this side our AC current waveform, with the DC and the AC. And then on your right side, we just have your power, speed, and torque. Cool. So I'm going to do two demonstrations just to quickly show you. The first one I will do is just a normal flat road test. So the reason I clicked flat here is because on normal driving situations, you do have some friction, you do have some wind drag, etc. So it's not just a free spinning wheel with the chain. So we add some slight load to that. On this side, you'll see the speed increase a bit, the torque increase a bit, power, and then you can just have a look at the waveform. Important on the waveform side, you'll see its period, and then you'll see the amplitude of the waveform also increase as I'm giving it some power. Okay. You'll slightly notice here at the bottom we've also got an efficiency or consumption counter that actually accumulates this over time. Secondly, as I mentioned earlier, we can simulate environments. I'll do a quick uphill simulation for you. Actually, let me do that while I'm driving. So the simulation we're going to run from just a normal flat, then I'm going to put it in an uphill situation where we're now going uphill. You'll actually hear the motor working harder, we're feeding it more power, and then you'll also see an increase in the values up here, more power getting driven and the torque also increasing. Okay, and then a final simulation I would like to show you to show regenerative power is going downhill. So in this case, it's basically we're freeing downhill. Can be faster, can be slower. And then the principle of using the motor or your inertia to actually give electricity back into the battery. So you see, I'm not driving. We're going downhill now. This is totally inertia driving it. Then I'm going to touch the brake pedal. Notice the power and the regenerative power going back into it, and our waveform increasing as well. And then important, the DC current now going negative. And then we're just back to a flat. Yeah, so this is in essence what we built for training, educational purposes, for people to just understand the principles of electric, of the motor, and how EVs work, because this you can transfer to a vehicle, to a bus, just on a bigger scale, on a bigger motor, on bigger batteries. Yeah, I think that's it from my side. Chris?
So one of the questions we get asked most often when we do training is people are worried about maintenance and technicians in the country. This is actually a crucial feature. And I think just looking at this bench, that is the essence of an electric vehicle. Maintenance is not a concern. It's really easy to swap things out. All you need is basically a high voltage license, and then you can roll with it. But I think this conveys the simplicity. If you had to build an electric, or at least a diesel or petrol engine onto a bench like this, it would have taken ages and it would have failed all the time. This only fails once a week, which is fantastic.
All right. I liked what Tinus was saying earlier, where he said that the main reason why we started in skills development was because that's where the money was at, and we really needed money at the time. But that is definitely not what drives me to do this research on a day-to-day basis. What drives me to do research on skills and training? I think we're on the cusp of a new revolution. If we look into history, we had the French Revolution, political revolution, which changed the dynamics of society. We then had the Industrial Revolution, like early 1900s, which changed the nature of work, and now we're on the cusp of technological revolution with the advancement of computers, of course, and AI, EVs, and all of this. And it becomes this, there's always been this tension in history when all these revolutions take place between, if you look at the French Revolution, it was promoting liberty, libertà, and equality between people. And they're always in tension. You have the communists with the, proclaiming equality, and the capitalists trying to get liberty. But the only way to marriage these two somewhat contradictory things is through fraternity and working together, solidarity. And so skills for me is really that education is really this aspect of coming heart to heart with one another to build up people. And I think that's really important in this technological revolution, where it's very tempting to focus on metrics. A person is a product of their efficiency and so forth. And so in this, what we're really trying to do here is to, in the South African context, to develop humanity, develop the society, as well as develop each individual man and their dignity through training them. And if we look at the EV market now in general, or the automotive sector, it contributes 5 to 7% of the GDP in South Africa. Depending if you include like the automotive services in that. And most of this is from legacy automotive manufacturers, like mostly from Europe and Japan. And it's very much in a crisis. As you may know, a lot of these manufacturers are under pressure to reduce the number of employees to try and compete in especially the new Chinese manufacturers and the advent of EV and their lack of traction in the EV space. So it's in this context that we're trying to develop a program that can boost the skills development in this country, particularly in EVs. And yeah, so how are we doing that? So we're following this approach called the ADDIE framework. It's ADDIE, ADDIE. So those are the sort of five steps along this framework. And it comes from an unknown author, but it's well used in the educational space. So if we start from the right, it's on analysis. So we first went into the industry to analyze what the need is. What are the problems that are being encountered by the industry? What roles are missing, and what roles need to be filled as we move towards electric vehicles. We then worked on designing a framework, like a course structure. We identified key topics that need to be, that need to be presented to meet the need that we found in the analysis. And currently, we're busy developing the course framework. I mean, we're developing the content of the course in an online platform, Moodle. And from the beginning of next year, if I'm correct, we'll be piloting this with maintenance technicians from TVET colleges to try and help them with basic skills development in maintaining vehicles, maintaining charging stations. And post the pilot phase, we'll be evaluating that and then repeating the development of the various other topics that we want to build into this whole course framework ecosystem. So this is not something we can do on our own. It's, we're developing the framework, but there are several roles, roles from various industries that need to, that we need to serve through this framework. So we'll zoom into the first step, which was the analysis. So when we approached the industry, and many of you might have received our survey, which we sent last year, we basically sought to find out 5 key questions. What skill areas, what topics are of interest for the industry? What is relevant? Is safety, battery technologies, motor technologies, and so forth. How do these different topics weigh in terms of the relevance and importance for various for the industry in general? And then secondly, also across various industry sectors, because you would imagine a manufacturer would have different priorities than a policymaker, even though they're still working in the EV ecosystem. We wanted to see what the current skill gaps are, if any, in electric vehicles, upcoming skill gaps, and the underlying challenges, the root causes behind these skills gaps. Yeah. So we sent that through to the industry, and we got responses from various industry sectors. Our main respondents were from the energy and infrastructure space, education, and policy. And I think there are quite a few policymakers here, so thank you very much. Manufacturing gave sort of an average, they were sort of the average median respondent. Yeah. And then we went on to sort of, I think this is very important because the results need to be sort of interpreted with this in mind, you know, because these are the people who are responding to our questions. So the first research question was, what is the relevance of various skill areas? And the 50% of the respondents indicated that data, the data analytics kind of topic was the most relevant for them. Then we had 46% in charging and infrastructure and 40% in policy making. But the main one was data, and I'm going to touch on to that a bit shortly. We then, you know, sort of looked at that across the various industries, and found that you know, different industries had vastly different needs. I think one of the key ones, for example, with policymakers, we found that you know, all of them responded that they needed skills in policy and regulation, of course, and 50% were looking at procurement and ownership of vehicles, how to manage that. I think I do have a list of the topics. Let me just see. Yeah, so these are the various topics that we had presented to the industry, you know, to identify which ones are more important to them. Yeah. All right. So we then went into the various industries and asked them, you know, do they have EV-related roles that they need to fill today? Policymakers said yes, overwhelmingly. So the dark red is the yes and the light red is no. So policymakers, they're forward-looking. They're trying to develop the policies now. And we got an overwhelming majority saying that yes, they're trying to fill roles and they're difficult to fill. The manufacturing industry, 100% of our respondents said no, they're fine as they are, which could be a point of concern. Yeah. These are the various industry sectors that we approached. So it's really across the whole ecosystem, from fleet operators, policy actors, manufacturers, really everyone. And we just put it out there. We sent it through our networks and also on LinkedIn. So it's a kind of a random kind of pool set that we got in developing this. Yeah, and so we were then able to map the industries to the skills that they need and sort of lump, you know, certain skills across various industries, you know, based on how they had responded to their skills needs. Yeah. Okay, so we then zoomed into each industry and broke that down into various roles, key roles that, so we had the previous map had 10 industry sectors, and we found 13 key roles that sort of map onto these various industry sectors. So these are kind of general, you know, the roles that we want to be able to upskill. So you might find yourself here. Unless you're an educator, then an educator has to fill in all the roles or whichever roles that they're trying to educate in. And so we developed a framework where each role has to, you know, we developed the topics or modules that they need to be able to be competent in. So for example, an EV maintenance technician would need to fulfill modules 1, 2, 4, 5, and 11. And these are the topics of those modules. So an EV technician would need the EV fundamentals, the electricity fundamentals, motor technologies, or and I think 11 was safety. So we're trying to currently build up these modules into individual like short courses, and people of the various roles, job roles, can pick out whatever modules they find are relevant for their particular case. Yeah, so we're currently developing this, and for our pilot phase, we'll be developing just the modules that are needed for EV maintenance technicians, and then in subsequent years, we would build out the remaining modules, based on the other key roles that we perceive that need to be served in the industry. So this is published in an article, all of this information that was sent in the handout that you may have received by email. And yeah, so we're currently building out this course in Moodle, this online platform, and hope to serve you or the industry from next year and the following year. So yeah, looking forward to working with you on this.
Thank you. Now we're switching over to two very important topics. I'll hand over to Wynand in a second. When we met in 2024, some of you were there as well. When we walked out, I set a challenge to Dr. Stefan Botha. I said, I want something produced locally. So he's going to talk immediately after Wynand about a locally manufactured, locally designed electric motor, which is a replacement for the motorbike. Because we do have the skills here, but I'm not sure for how long we're going to have the skills here to do that thing. We want to demonstrate it. And then now the other part is something funded by the Western Cape. It's something that Karel and Antoine Yassine, they insisted we do, and I'm very glad again that they did. He's going to talk about battery assessment. So he's supervised and unsupervised by Dr. Rix and Professor Rix and Dr. Strauss. And this is about assessing the quality of batteries and understanding what is being dumped onto South Africa and how well these cells are performing in different conditions, because our conditions are different. So I'll hand over to him in a second. I just want to fix the streaming has stopped and people are complaining.
Everything okay with the mic? Right. Good morning, everyone. So I want to tell you about our research in the battery research group, just what our motivation was for starting the group, what we are currently doing, and what we will be doing in the future. So a significant obstacle that we have identified in batteries driving electric mobility is just the lack of data. There's not enough data available publicly or regarding the different chemistries that you can use, the different packs, the different sizing, in the different geographic areas that you can use these batteries. So our aim is to create those data sets and to create massive data sets on the different chemistries, current chemistries, future chemistries, current technologies, future technologies also coming up. So currently where we are is, this is the equipment that we are using. You can see on the right-hand side of the screen, there's an environmental chamber. That environmental chamber can control the temperature from 60 degrees Celsius down to minus 20 degrees Celsius. So that can simulate a vast array of geographic conditions. We can cycle the temperature, or we can keep constant temperatures depending on what the needs are. To the left of that, the two black boxes are bidirectional power supplies. They are commercial programmable power supplies. So we can both source and sink power from batteries and thereby simulate real-world driving conditions on the cells. So we've got 8 channels, which means we can cycle 8 cells at any given time. And they are completely independent from each other. So every single cell that we are cycling can receive its own individual drive cycle or conditions. We can look at different C rates and more or less aggressive drive cycles. We are currently undergoing a cycling campaign where we cycle 18650 lithium cells, so 8 of those. And what we are doing is we're using the WLTC drive cycle. So that is specified by the United Nations. It's a standard drive cycle that simulates or indicates low, medium, high, and extra high driving conditions. So it's defined in a speed range. So that's what you see in the top chart, and the bottom chart is what the battery sees. So everything atop this horizontal line is discharge from the battery. That's from acceleration or cruising. And below the line, we're looking at regen towards the battery. So that's under braking or coasting conditions where you can recapture some of that data. So this is just the first versions, what we are working with. We're also currently working on a second generation environmental chamber, and we will be moving from commercial power supplies towards in-house designed cycling systems where we can look at more cells, bigger volume, more capability. So here's some data that we've started seeing from our current cycling campaign. We're about 2 months in. We are cycling the 8 cells, and we have grouped them into groups of 2 cells. So every successive 2 cells are undergoing different cycling parameters. And we're already seeing some interesting things happening throughout the cycles. We are keeping a constant temperature, and that's just because of the chemical nature of these cells. It's different at different temperatures. So at a temperature of 25 degrees Celsius, we are running that WLTC drive cycle. From a fully charged cell, it's a 30-minute cycle, so we just run it repetitively until the cell is discharged. Then we refill the cell again, and that is one cycle. So we consistently run that. But we're not limited to that specific drive cycle. We can simulate anything. We can do put together a bunch of different drive cycles and data sets, so we can simulate a specific route for a bus or a motorbike that it drives. And that's just on the driving side. We can also look at different applications. We can look at peak shaving and grid support batteries, or we can look at data centers or residential housing. So it's not just limited to electric mobility in that sense. This data is just scratching the surface, however. We are already looking at, from the current data that we have, there's a bunch of different directions that we can look at, a bunch of different insights that we can glean. And an interesting thing that we've seen from this data is it's actually raised more questions than we had when we went in. So those are all questions that we will try to answer by processing the data, and also with future cycling campaigns that we will be doing. We'll try to answer these questions that have been raised. Look at the future of the battery research group is our second generation of the temperature chamber and the cycling system that we have. So here we've got our temperature chamber. You've got the 2 drawers over there. There's a close-up of the drawer, and there's actually a cell in its holder. So we will move from being able to cycle 8 cells to 48 cells in this configuration, and we've already started manufacturing this temperature chamber. It will also be able to control the temperature, but we are aiming to introduce humidity control as well, because that affects the performance of these cells. And that will allow us to simulate a wider array of geographic conditions. That won't be the end, however. We're already conceptualizing future environmental chambers and platforms and capabilities for our systems. We are aiming to be able to cycle, to build chambers that can cycle more than 200 cells, and also complete battery packs on top of that, so that we can look at about what the dynamics are between packs and cells. And we will also be introducing shaker beds to simulate the vibration that these packs will experience in the field and investigate a bit more what we can see in that sense. So what we can do with all of this data is we will generate the data sets, and as you've seen here, everything is driven by the data. We make the predictions, we make the decisions from what we see in the data. We will be able to support second life applications of the batteries, and we will also be able to, if you have an application in mind for batteries or for vehicles, we can look at simulate first up in our temperature chambers and environmental chambers what chemistry will be the best to apply in your specific case, and that can potentially drive cost savings and efficiency. We can also perform optimization of our operations and our industry partners' operations. So yeah, that's a brief oversight of what we are doing. Yeah, thank you.
I was at Coventry University in June, I think it was, and they took me to their battery facility, and they had a battery testing facility that he estimated costed them £200 million. So I want to contextualize what these guys are doing with small change relative to what they're doing. It's really amazing work. But on the same side, I just want to thank the Western Cape government. I think without your input, none of this would have happened. And again, we would not have been on this trail of learning and extracting knowledge. So as I said, next up is our localization motor expert, Dr. Botha.
Yeah, good morning. My name is Stefan. Can you guys hear me? Today I'm going to be talking about something that we don't like to admit. When we're talking about we're building EVs anywhere in Africa, what we're actually saying is we're buying from China and we're slapping it on and bolting it onto a different frame. That is not what building locally means. The problem is that China is by far the largest producer of everything. When it comes to motors, inverters, batteries, everything, China controls basically the entire supply chain. One thing about ever moving this sort of production to sub-Saharan Africa, South Africa, is always going to be a case of supply chain resilience, whereby if we wanted to go for more exotic materials and technologies, we are fully reliant on having to import every single bit of it. So that's why some of the research that we've been doing has been focusing on what are the technologies that we have from industry here right now? What are the industrial capacity that's available? Because we're already building motors and inverters and stuff for standard commercial applications, so standard induction machines and synchronous machines. We are building them locally already, but we are not building any EV motors whatsoever. So part of that was then to do two different prototypes. So one is for the Rome electric motorcycle. So it's a 6 kilowatt prototype. I've already finished testing it on the dyno. It should be finished on the bike towards the end of this month. And then we'll know what the sort of range comparison is between that and the Rome electric motorcycle. And then the 90 kilowatt prototype has already started manufacturing, should be done by end of October, beginning of November, around about that time. But the key part of this is we're trying to use everything that you can use in South Africa. So all of the coppers from here, all of the steels from here, the casting is done here. The only things that we're buying is the bearings. Everything else we actually make in South Africa. And the funny thing is that we have the industrial capability. This wasn't a machine that was assembled downstairs by our people. This was sent out to industry. Industry fully built this motor according to our specifications. And they can scale this up to be a lot bigger than what it currently is. Now, you're always going to have some trade-offs when you're going to go for a little bit different quality of materials, especially when the materials that we have are a little bit lower frequency, mostly centered around the 50 hertz applications. But you can still theoretically get a fairly decent drive cycle efficiency, even when you go for either a small induction motor or a one-rotor synchronous machine. You can still get away with getting 95% of the way there and doing it all in-house locally in South Africa. Now, one other thing that we're going to move towards, and this is more a little bit in the future from now, is that eventually as we adopt more electric vehicles, be it small ones, big ones, doesn't really matter, we're going to sit with a whole bunch of perfectly fine motors that we're not going to use, especially when cars are being crashed, when they are reaching the end of life of the battery and it's just not worth it maybe to replace the batteries. We're going to sit with motors that are still perfectly feasible, because these motors, they last 30 plus years. So one thing that we've been looking at is to repurpose these for micro wind turbines. So the whole idea of it is can you take these motors, build a wind turbine really cheap, and go put it somewhere rural where they need it? Because as EV adoption is going to go up, their demand in rural areas is going to go up a lot. So the question is, can we realistically build some small turbines to support these local industries and these communities? And the answer is, experimentally, it says, yes, we can. We've got 10 motors from Rome that were decommissioned. So they either had faults in them, sensor faults, winding issues, bearing problems, that sort of stuff. We've recommissioned 7 of them for a total cost of about 400 Rand. So it was pretty cheap to actually recommission these. We've already tested them as a generator. Now the next step of it is to actually go put it on a functional turbine outside somewhere. And they can generate anywhere from about 2 to 3 kilowatts of power, depending on the area, how much wind you have. I mean, if it's not a windy day, we're not going to make much power. But the big thing is, when we are looking towards this and looking towards the future of this, is what can we do here? How can we move away from just buying everything from China and being fully reliant on them basically holding us captive and us not being able to do anything? All right, thank you, that's it.
Okay, so I'm with you in one day. You can swap over here. So I'm currently affiliated with 2 departments in the university, Department of Industrial and Electrical Electronic. And the head of Department of Industrial said I should tell you, due to funding constraints, we've actually had to close our workshop. So we're in a position now where we're really on the edge. So if you guys are sat on money or know of something available, please do, because we're effectively terminating probably end of the year if something doesn't come through. All right, and that's basically why I invited the whole of City of Cape Town to come and see the death of our monster. Yes, so next up, Joe Anderson from the City of Cape Town. They are the reason why we're here today. They wanted to see some of the stuff we're doing, which just warped into this weird event. She asked for a moment. I have no idea what she's going to say. Thank you.
How do I make this go on the screen? That's what I'm going to say.
That's a good thing.
Thanks, Tianis. Thanks so much. And thanks so much for having us. I'm sorry about all the back and forth. It was cancelled at one point, and my travel report was only approved at 8 o'clock this morning. So it's great to be here. And it does sometimes feel like we live in a completely different world within the City of Cape Town. And I have to keep reminding myself that we are completely immersed in like an EV lab, which it's great to see all the work that's been going on. So I sit within the Energy Directorate within the City of Cape Town, and our little unit is called the Sustainable Energy Markets, and it's a group of about 30, 40 individuals, and our role is really to set up, to look down the line in terms of the future energy and how do we as a utility provider in terms of energy start to navigate the future of how energy is provided to all our customers within the City of Cape Town, which is not you guys within Stellenbosch, but that was really the role of our department. And so EVs and the future demand that EVs will place on the grid is a key part of our work. There's a whole lot of other work going on around how the provision and the unbundling of Eskom, etc., that is also dominating our work. And so working within the city, there's a lot that goes on. And the EV work really is like a bit of a virus. It just gets hold of everybody. Everybody's quite interested in it. And there are so many different moving parts. So it's hard to get a handle on all the research and all the implications for the city. But basically, the city has got quite a strong drive to support EVs. Our role is not necessarily that we've got fleets, obviously, within all the different directorates and departments. There's the bin trucks, there's the cherry pickers, all those, and then there's safety and security. They've got more sedan vehicles. There's a whole focus on transitioning of those fleets, but that's complicated in itself. And then our role, and my specific role, is much more enabling the market to support EVs, whether it's working with EV manufacturers or installers, or with support particularly on chargers, because our work is specifically how those chargers integrate within the grid and what the impact is. So obviously we work on a much bigger picture, and this is just some of our reporting that we do, and this is just around understanding the impact of the emissions of the vehicles. You can see there the on-road transportation by sectors. This is obviously within the city metro is 24%. And then if we look at our actual emissions for the local government, you can see that local government is only a very small percentage of the overall, but within that the vehicle fleet is 15% of those emissions, which is actually not too bad. But it is, it's just understanding, what order of magnitudes of emissions are we working with. And then there's a little deep dive into the energy consumption of the sector this is the transition from 2019 to 2023, just understanding, where we can have greater impact. This is a city-wide diagram. It's not looking at the local government existing kind of fleet. And then just also, I've mentioned the fleets that our corporate services, etc., manage, but we've also got a My City bus network. It's been great to hear from Gabs this morning, and that is also, a transitioning to electrical, but slowly. I'm not going to go through all of these slides, but also over the years, the city's done quite a lot of research, but obviously not to the depth and technical kind of expertise that's been presented today. But as a city, we kind of needed to understand what is going to be the uptick of electrical vehicles and what is the potential impact on the grid. This was quite an old study that was done that was just saying that there's an uptick 2035. Look, I think now the crisis with regards to the fuel prices is probably a little bit out of date. One of the things that we're grappling with is at the city is what role do we play in terms of the public charging? Do we just leave it up to the market? Or do we say charging infrastructure, grid cars, etc.? This is where you can charge. This is how many charges we want to see. And how do we start to navigate that role that we play within the charging landscape within the city? How do we start to build customers? Is there one sort of, how does the technology work of somebody rocks up to a charger? Is there sort of policy or regulation around how the communication works with the charger and the individual charging? And we've done a number of studies and sort of research to different cities to understand what this role of the city is in enabling this kind of infrastructure. And we still don't really know. So this is a little bit old now, and I actually don't want to go into too much detail because there's so much technical kind of information in the room. But basically, this was a study that we did with Green Cape that looked at what if we took our fleet vehicles, which are mostly sedan vehicles, and we transitioned them from ICE to EVs, what would be the best kind of vehicle? And we did this with the BMW i3 at the time. But the main outcome of this study was that we can transition the fleets, but only as the kind of research has been shown today. It's not a one-for-one kind of transition. It depends on what that vehicle is being used for. It depends on how it's being driven. It depends on the type of vehicle, etc. So transitioning our fleet is really dependent on what the vehicle is being used for, when it's being driven, etc. And then this is also quite old, but through UNIDO funding, we had two installers two charging facilities installed at municipal facilities, and the aim was there to sort of gather information around charging behavior, and this was really these were solar PV, so this energy was free. There's not a lot of vehicles that come and charge at municipal buildings. Not surprising, everybody wants to charge their vehicles at a shopping mall. But this just gave us an idea of the sort of charging behavior and how that can be complemented with renewables. This is our one electrical bus that we have in the fleets. But interestingly enough, this often happens within the city. It's a massive organization, and it does tend to be siloed. But they had an order in for the electric buses, and I think there was a real challenge into getting the energy demand into the depot site where all the chargers were being installed, because it was an Eskom area. So it's much easier if anyone is in the bus thing to charge, to work with the city of Cape Town in terms of your electrical supply, because in the end, what we had to do on the site is do an arterial tie so that we could get the supply from a city of Cape Town side, instead of diverting from a substation that was 5 kilometers away, to get the additional supply to the site. And those kind of challenges are the challenges that we are trying to optimize from a grid perspective, as where are the sites that we would like to see depot charging. There is an extreme demand that gets met. And then also a lot of the work is how do we incentivize what we call not dumb charging, so that everybody comes home and plugs in their EV. How do we, design the tariffs, or how do the vehicles work in that they're a smart vehicle, in that they read the cost of the electricity and they only charge when it's low demand and therefore low cost. And all of these kind of challenges are what we're trying to grapple with at the city. So obviously a lot in the city, we do a lot of awareness and stakeholder engagement. We run quite a lot of comms. I'm not going to go into all of this detail, but we've got 2 big groups within the city, and the one is the SteerCo, which is all our executive directors, and they give direction around electric vehicles, and that's where a lot of the drivers come for the uptake and the enabling of the EV network. And then we've got a working group as well that works more on the ground, and then we've got quite a lot of stakeholder engagement that we do across in and outside of the city. And then just a quick note on looking forward. We did a nice event. This was with Flix, I think, where we looked at trying to support charging of taxis at PTIs. Where are the city-owned PTIs where it is close to city supply, where we can support charging of minibus taxis. This was interesting in that there's a charging at Century City, and it was very interesting spatially how that would have to be managed. Part of the PTI, it needs to be a separate kind of managed area, so that the charging can be managed. And that was a very interesting finding. We kind of haven't taken this further yet, but that was, if we're going to support the transition to EV, I think the public transport is definitely a focus area. This was also just understanding the EV charging. I've mentioned this already, but this was also around how do we as the city, so for example, the rooftop solar applications that we have within the city, we've had to regulate how people connect to the grid, and we're foreseeing something very similar with an EV. So how do we start to regulate? I mean, without burdening with admin, but it just does have such an impact on the management of the grid when you've got all these massive loads coming online at different times. And how do we start to incentivize not dumb charging, and how do we develop to say, like, these are the standards that we require if you are going to charge, plug into the network, and then there is the vehicle to grid also. If you are going to use the battery power within the vehicle, how does that feed into the grid? So that was looking at what standards are available and what kind of best practice we could recommend. This was also mapping demand for the public transport. Here we worked we looked at all the substations within the city and the demand within those substations, and then we looked at like GABs, bus networks, and where the depots are positioning themselves, and how we would have to upgrade our substations to accommodate particularly the depot charging. That was actually the findings. All these reports are publicly available if anybody finds them interesting. And this is what we're developing at the moment. We're trying to develop this sort of best practice. I think one of the challenges for us from the SAND side is that the vehicles are seen as an appliance at the moment. So that's one of the key challenges that we are, and I think that the standards were noted earlier in that we've got these very European standards, and applying them locally is quite challenging. So yeah, that's a kind of wrap up of what we're doing in terms of EV, and my particular challenge at the moment is that our team has been tasked with understanding where do we put chargers, how do we tell the market where we want these chargers and how many, or do we just leave it up to the market? And that's really where we're sitting at the moment. And then I think in the room is represented also by fleets. Maybe they can add in as well as the MyCity network. And that's it from us. Where it comes from as well. Thanks.
Thank you. I didn't want to put it on the spot, but it's awesome to see them on the spot, isn't it? City on the spot. I want to share a few more slides and then we can head to lunch if you want. I think I want to highlight a few things. The first thing I want to just say is downstairs, when you enter the building, you'll see there's a converted vehicle. So we've converted this with support from Hydac and Balance Cell. Balance Cell gave us the batteries, Hydac gave us the motor and the inverter and the stuff. Just stop this nonsense. There we go. So you can go and look at it. If you want to, you can even do a few donuts on the grass. I don't care, I'm a professor, they can't fire me. But this is really an example of excellent engineering happening right here. We're trying to get rid of the vehicle. So if you want to buy a vehicle, it's quite expensive, but you can have it. We've also converted this vehicle, but Waldo forgot to charge the battery, so it's parked in our lab, or at least what used to be our workshop. Waldo can try to get it around the corner again, charge it, bring it around. But the other things that I want to say is maybe just what is apparent from what we said this morning. It's really not about the vehicles. It's to a large extent about the infrastructure. And I think just linking on to what Joe said now, what Joshua's research has shown, and he kind of hinted at it, but that's very important to hear, is you don't need fast chargers. You need charging opportunities. You need places to charge slowly, because that's the best for the grid, that's the best for the batteries, which is the most valuable asset in the vehicle. In his research and Brendan's research, we found that if you just install chargers, for example, at the informal stops where the taxis stop, you all of a sudden have this opportunity of keeping their current mobility patterns. They can keep driving exactly as they are, as long as you present them with charging opportunities at informal stops, rather than thinking malls, thinking formal taxi ranks. That's the one part. The other part is, if you allow them to charge at home, then everything just works out perfectly. But they can't charge at home because our informal settlements can't support that level of electricity supply. One of our colleagues here, who's not here today, Bernard Bakker and Justice Chihota, they've actually done research that shows in some of the cases, if you plug a single taxi into a street supply in Kaimandi, the whole street will lose power. It'll literally blow up the infrastructure. So we need to carefully think about this, because it's to the benefit of everybody if we provide proper infrastructure in the townships and then allow them to charge their vehicles there. Because I think you can all see where this is going if we don't. When I mentioned to the taxi drivers yesterday, it was yesterday, Gavin? Or Tariq, I think so. I was there yesterday. Sorry, my life is a mess at the moment. The first thing that I said, well, you can charge your vehicle anywhere, and even if you tap it illegally from the electricity infrastructure, that is fuel. Their eyes went like this. It's a fantastic opportunity if you're driving an electric taxi to charge from stolen electricity. It's free. Why wouldn't you? And that's going to be extremely detrimental to all of us, every single one of us. We need to carefully think about the planning of the infrastructure. The last thing that I'll share before I share, I hope you guys don't mind me sharing this, but the Western Cape government has been engaging with a supplier to install charging infrastructure for their fleet. They sent them away, and what they came back with was a huge battery bank to provide 4 hours worth of charging in case of 4 hours worth of load shedding. And what I'm trying to convey when I say this is, if you ask an electricity supplier, or at least somebody who's an expert, fudge, this is too bad. Just turn on the volume a bit. If you ask somebody who works with electrical infrastructure and who thinks load shedding all the time, come in and help me with chargers, they're going to put down something that you don't want, that you don't need. We very much have the two worlds colliding of energy and electricity and transport. And you can't ask just one of those polls what the future looked like because they can only see half of it. In fact, Gideon said the other part. We can't just think mobility and electricity. We have to think health. We have to think well-being. We have to think all of those things. Environmental. It's not useful to have one-dimensional spectacles on and think in silos when you think about transformation. So fortunately, the Western Cape government said, hey, hang on, stop. We're going to tell you what we need. And then the electrical guy could come in and say, this is from an electrical perspective what's required. And then they brought in a transport guy. This is what the transport aspect is. So now it's a whole picture, and the solution will be to the benefit of everybody. So I think that's maybe one of the core messages that need to come through today. And on that bombshell, lunch will be served in 10 minutes' time. Can I ask, we have 10 minutes. Are there any questions? Yes, Gideon.